1% better every day, building search from prototype to production. Hi, I'm David, and I'm a principal architect here at Algolia. I actually started out live as a mathematician working on computer algebra, but then I later co-founded Search.io, which was acquired by Algolia in 2022. So for the last 10 years or so, I've been designing and building AI-driven search engines, thinking about everything from the UI in the front end all the way through to the bits and bytes that are stored on disk in the search index itself. So by way of introduction, I'm going to let you in on a little secret that I've learned along the way. And that is that there are no silver bullets in search. So what do I mean? There is no single idea, technology, or strategy that's going to come along and just solve search. Instead, good search is a mix of many different ideas, technologies, and strategies. To get the best results, you nearly always need to do quite a lot of work. So maybe think about using models for query understanding and augmentation. If you can classify the query, maybe you then want to switch to a few different strategies. You might also need multiple retrieval systems, keyword, semantic, or even image. And then, once you've worked out how to merge all of that data together, maybe apply multiple different ranking signals, and then some personalization. And then on top of all of that, before you pass it back, you might want to put it through an LLM so that you can have a more conversational style response for your users. So this whole process can be pretty complicated. To make it work well, there needs to be a lot of planning and coordination. And so we call this query orchestration. So here's just a glimpse into some of the pieces that make up our search system at Algolia today. Every item here brings value in a different way. And so you can start to see that it would be very hard for one new thing to come along and replace it all. Okay, so when you are prototyping something, it will typically fall into one of three categories. You can iterate on an existing component, you can improve how existing pieces work together by rearranging them or maybe being smarter in how you combine them. And finally, of course, you can actually just add something completely new. And with that, you likely also have to decide when you're going to use it and how you're going to mix it in with everything else. A great example of this actually is semantic search. So about 5 years ago, LLMs started to get really good at encoding the meaning of text into vectors. Combine this with a vector search, and you can suddenly run queries that match on the actual meaning of the words rather than just a keyword overlap. So conversational style queries, where you might not know exactly what you want but can describe it, were suddenly possible. And so this turns out to be really useful. Unfortunately, this relies on your model knowing about the words in the query. And so things like lesser-known brands or product names could fail completely. Also, things that don't actually have semantic meaning, so part numbers or SKUs, don't work either, because the model has nothing to map them to. And so now, even 5 years later, with all the improvements that have been made to vector models, and also things like fine-tuning, we still don't use semantic because it's just not practical for all the use cases that we cover. So this is a great example of where you can't actually replace anything. Instead, you need a combination of both the old keyword and the new semantic for the search to be most effective. And this really is the reality of no silver bullets. Your system is only going to get bigger and more complex as you chase improvements. So prototyping here is very tricky. To add something new, you need to work out how you're going to integrate it with the rest of the system, and also when you're going to use it, or maybe even what kind of queries or use cases you're going to apply it to. On top of that, you also need to be aware of practical considerations. You're putting something new in. Does the added value justify the extra complexity? More CPUs, more memory, more resources to spin up and manage. You also need to be careful not to impact the reliability and latency of the queries that you're already serving. So there's a lot to think about, and a lot of these questions can be really hard to answer in the prototype stage. If your idea turns out to be amazing, you might find that you have lots of engineers to help you with these problems later. But when you're starting out, you don't necessarily know where it's going to go. So how do we go about this at Algolia? To get a prototype through to production, in our query orchestration system, we follow a process that we call a learning loop. So basically, it starts with a new idea. So let's say you've seen a bunch of search results that aren't great, and you have an idea of how to improve them. The first thing you need to do is actually just try to make your idea work for those queries. So starting with the current production behavior, you add your idea on top and eyeball the new results. So let's say that you're happy with these changes. Now you need to make sure that by fixing those few bad queries, you haven't accidentally broken anything else. Replaying historical data is the best way to do this, but if it's not available, you can generate some synthetic interactions via an LLM and run those instead. If something's broken, it should show up now. Now, finally, once you're satisfied that it works, you need to actually ship it to production, so you can start to see how it behaves in the wild. Assuming then that all is well, the cycle continues. Okay, so when new things come along, we want to be able to try them as soon as possible. The more ideas and tweaks that we can try, the more improvements we can make, and therefore the more successful we should be. We need to make it easy to follow this loop, so that we can concentrate on innovating instead of just pushing code around. But enough talking. Let me just give you a quick tour of the internal tool that we've built to enable this inside Algolia. On the left here, we have a query algorithm, which is just running a basic keyword search. And on the right, we have a search interface that you can use to run searches. So you can see it seems to be working nicely. This is just a demo set. But the results look pretty sensible. So let's just go ahead and change the algorithm to overwrite the query so that we can just see that this is actually working. So if we run that again, you can see now, no matter what you type, actually the results are the same because we're overriding the query. So it's a bit of a silly example. So let's just try searching for something a bit more conversational. So something to write with and see what we get. So you can see here that keyword's actually struggling to produce a good set of results. And so probably what we want to try is maybe looking at vector. So we have another little toy example here, which is running a vector search. And so you can see immediately now, actually, the results are a lot better. These things actually look like pens and crayons and colors that you could write with. And so over here on the left, the algorithm is constructing a vector request, then running a vector search, and then actually just returning it to the user. But as we were chatting about before, when we're looking at semantic, typically you actually want to merge it with keyword because there are some use cases where it doesn't work. And so how do we do that? Well, we can actually take the pieces that we've just used. So you can see here that the result sets are now actually merged together. And what's going on here in the algorithm is in parallel, we're actually running a keyword search as we did before. And then we're also at the same time running a vector search. And then instead of returning it, we're actually merging them together. And so this is basically just concatenating them. And then we return it to the user. And so you can see over here that the keyword results are appearing first, and then the vector ones are following. So actually looking at this set, probably what you want to do is put the vector results first, and then the keyword. And so you can just quickly try that and see that actually, yes, it does make it better. Okay. So how about we try and build on this even more and just look at a different example. So what about something like RAG? So as you can see here, we're expecting a more conversational input from our user. And so we're running a vector search, just as we did before in the previous algorithms. But now we're also writing in the algorithm a system prompt and a user prompt and filling in things like the user query. And then when we get them back, the search results, so that we can actually pass it all through to the LLM, which will generate us a much more conversational output that we can, process and then send back to our users. And so you can see here, actually, it's done a pretty good job of doing that, and all by using the functionality we had and just adding a very little extra, which was just this call out to an LLM. Okay, so how did we get to this? As you've seen, it was very easy and quick to make changes. We prioritized designing for engineering velocity, which basically means we stopped trying to build individual query algorithms and instead built a system to build query algorithms. So let's break it down. To make it easy to try things, any functionality that we might use as part of a query needs to be completely composable. So for example, running keyword or semantic searches, merging and ranking result sets, but also things like looking up configuration or generating text with LLMs. When you have this, then your search algorithm can be made of a sequence or graph of these pieces. And so, with this composable system, if you can represent your idea using the pieces you already have, then you can get it up and running in a matter of seconds. It turns out that with just a few well-defined building blocks, you can prototype most things really quickly. And now that the algorithm is basically a piece of config, you can just pass it along with your query and give it a try without touching live production traffic. We built this environment from scratch, so we get to decide where the boundaries are. It needs to be just flexible enough to be useful in search, whilst having safety nets in place so it's hard to make mistakes that could cause problems. And note that when I was making changes earlier in the system, I didn't actually have to ship any code to try anything. And so you don't have to be an engineer to do it. In fact, we've seen CSMs and product managers make changes here that have ended up going all the way through to production. Being able to try something quickly and easily is hugely important. To help verify an algorithm, we have an automated simulation system, which unfortunately we didn't have time to show in the demo. But the key pieces here are that it's completely data-driven. So we take the new algorithm and run a bunch of historical data through it. And if we don't have historical data, we use synthetic data generated by an LLM. Since our algorithm is config, we can do this on the side without needing to touch or change the live production behavior. Running all the top queries of the live system means that we're basically performing a huge integration test of our new algorithm. And we can also then measure the performance of the new algorithm against the current prod, using metrics like NDCG and recall. If we've broken anything, it should show up here. So then in practice, it can just take a few minutes to verify a new idea. If it passes, you then have hard numbers that you can use to argue for further work, or even to move to a live production test. So, how do we ship it? Well, since we've been running in the production system from the start, just not actually serving live production traffic, we don't actually need to do very much. We just need to set up an A/B test that will point to our new algorithm and wait to see what happens with the live traffic. So the iteration speed is now very fast. It takes us seconds to try something, minutes then to verify it, and then seconds again should you want to move it to a production test. Now, of course, once it's in production, you'll want to leave it there for a while so that you can see how it handles new traffic. But there's nothing to stop you from going back in the loop and trying something else on top. You just have to be careful if you want to ship something that you don't bias the test. So now we have a very lean system for making changes, and so you can justify trying almost any idea because it's so quick and easy. And so trying small changes and taking them all the way through to production is a lot more viable, and this turns out to be a great strategy. When you're introducing something new, it helps you ship early, and then build confidence that what you're doing actually works and makes sense. It also makes changes a lot more predictable, and so easier to manage. And you can measure the trade-offs as you go. Both of these points are actually very, very important when releasing a new AI model. You can start to leverage new models as soon as they're available, whilst making sure that they don't run away from you. And with the data checks in the learning loop, you can be sure that you're not breaking things that you care about. Small changes can sometimes seem insignificant on their own, but over time, they compound. And of course, this is 1% better every day. So just to summarize, in a world where things are changing very quickly, the faster you can try things out and verify that they work, the more likely you are to succeed. So when you know that you'll be making lots of changes or improvements over time, invest in the process. And finally, although this does make for a great system for us humans to use, it's also a massive step forward to getting AI to start optimizing query algorithms. With a set of well-defined composable tools and a data feedback loop to keep them in check, we can safely start experimenting using agents to improve our search algorithms. Thank you.